Hi everyone, I'm Moretti. I'm a postdoc at the data science group in SISTA, where I work with Roberto Trotta and collaborators. And today I will tell you about doing cosmology with galaxy clustering, focusing in particular on the power spectrum and the bispectrum. So I like to start this with a little motivation of why we do this. And we already heard about this before. We are in the era of big galaxy redshift surveys. Stage 4 surveys are already ongoing and upcoming. And these surveys will scan the universe. They will give us the galaxy distribution over an unprecedented volume. And they will deliver high precision measurements of the observables. So in principle, what we hope to get out of this are answers to some of the very big open questions concerning cosmology. So the mass of neutrinos, we heard about that before. Also, do we have modified gravity? Are there tensions? Are the tensions that we see in the measurements real? And where do they come from? And in order to answer these questions, we need to fully exploit the power of the data that we will get. So we heard a bit about machine learning, and I'm sure that will play a big role in the future. But for now, I will focus in this talk on the more standard way that we extract cosmological information from galaxy surveys. And that is to usually we look at the galaxy distribution and we correlate the position of galaxies and we compute some summary statistics, and from that we perform a likelihood analysis and we obtain constraints on the cosmological parameters. But in order to fully harness the power of the upcoming data, high precision data, we need to go as deep as possible in the nonlinear regime of structure information, and also we want to go to higher order statistics. So not only look at 2-point functions, but also 3-point functions or a higher order. And this is where my work comes in. So to reach this goal, as I said, we need an accurate and fast theoretical model that is able to model nonlinearities. And then we perform a likelihood analysis to obtain the cosmological parameters. So to reach this goal, we develop a pipeline for the likelihood analysis of the power spectrum and the bispectrum. It's called ABJ, the code that we develop. And it features a power spectrum. It's code to compute the theoretical prediction for the power spectrum, which features one loop model based on this called the effective field theory of the large space structure. And I will say more about that in the next slide. It takes advantage of an algorithm called FastPT to quickly evaluate all the building blocks of the model, which are 28 integrals, and we can compute them in a really fast 30 milliseconds. Then the model requires the composition of the power spectrum in a wiggle and a wiggle part, and then an infrared resummation routine. And this is needed to properly take into account the nonlinear evolution of the BAOP. So in total, our power spectrum model has 11 nuisance parameters, plus, of course, the cosmological parameters. For the bispectrum, we have a 3-level model. So in a way, it's a simpler model, but of course, this is a 3-point function, so it's much more complicated to compute. We not only have the monopole of the bispectrum, but also higher order multiples. And also in this case, the code we developed is pretty fast because it can compute a theoretical prediction in 0.1 milliseconds. And in this case, we have 6 nuisance parameters. Some of these are shared with the power spectrum, but there are additional ones that concern the noise model that we include in the bispectrum. So this is it for the theoretical prediction, but this is a full likelihood pipeline. So it's the theoretical models are combined with different samplers that we use to explore the parameter space. We have a number of them, so you can pick the one you like more. And then we have also different likelihood functions that can take into account possible noise in the covariance matrix. So this was first developed here in Trieste by a group here in Trieste, and then with the collaboration of people in Bonn. And you can find some more technical details about the code in these papers. Right, so I will tell you a bit more about the theoretical model. I only have this equation, I think, in the presentation, so that's not too bad. So as I said, the power spectrum is a one-loop model with EFT counter terms. So basically, what we have is a linear or tree-level contribution, which is then improved with loop corrections, which have this form. So basically, these are integrals or convolution integrals with a kernel. And these two quantities, well, these are not two quantities. These are 28 integrals that we need to compute to construct the model. And this used to be the bottleneck of the theoretical computation in terms of time. But new developments, new algorithm allowed to take down the computational time to milliseconds, as I said. Then this model, this effective theory-based model, has some counterterms, and these are simpler to compute. They're not integrals, and they allow us to basically somehow include in the model our ignorance about small-scale physics concerning the structure formation. And then we have some prescription for noise. So for noise, we have deviations, possible deviations from Poisson shock noise, which are both scale independent and scale dependent. And so in total, this thing had 11 nuisance parameters, as I was saying, plus the cosmological parameters. Now, the bispectrum, as I said, is simpler in a way because we don't have loop corrections. This is a tree-level model. But it's a three-point function, so it depends on many triangular configurations. So we are correlating 3 points in space. So it will have a dependence on K1, K2, and K3, but also it will have a dependence on the orientation of these triangles with respect to the line of sight. So in a way, this is actually more complicated to compute, or let's say more costly to compute computationally. Okay, so once we constructed our code, we want to validate it, and we do that with a data set that consists of 300 embodied simulations. They were run with Lambda CDM Cosmology. They all share the same cosmology, but of course the initial seed is different. So what we do is we fit all of these simulations simultaneously, and then we combine the likelihoods. So effectively, what we are fitting is an enormous volume of about 1,000 cubic gigaparsec. This is unobservable, but it's something that we want to have in order to stress test the model and understand up to which scale it works, and also other possible theoretical systematics that we might be ignoring. This data set of 300 simulations is also it comes with a covariance that is constructed from 10,000 mock simulations. These are computed with Pinocchio, which is a fast approximate code to generate halo catalogs. And this is particularly important because having this very big number of mock simulations allow us to remove the noise in the covariance matrix. So for example, in this plot here, you can see the covariance matrix for the monopole of the power spectrum. And the top triangle is what you get from 300 embodied simulations, and the bottom triangle is what you get from the 10,000 Pinocchio mocks. So you see that all this noise is removed, and we are left with the actual correlations between the beams. And this is particularly important when considering the bispectrum. So in terms of validation, the first thing we do is we look at the nuisance parameters. So we have simulations, so we fix the cosmological parameters, and we only vary the nuisance parameters, which you can see here. And we do that for the power spectrum alone, which is the blue lines. And then we add the monopole of the bispectrum, and then the monopole and the quadrupole of the bispectrum. And we want to see, first of all, the improvement that we get when including the bispectrum, which is very significant for some parameters, not so much for others. And then in this case, we repeat the analysis as a function of the maximum scale that we include, the Kmax that we include in our analysis. And what we want to see here is when we, up to which scale the model works. And so what we get here is that for this very, very big volume, the model works pretty well up to a scale of 0.15 inverse megaparsec. Then we move on to cosmological parameters. So in this plot here, you can see the constraints obtained with the power spectrum alone in blue, and then with the addition of the bispectrum monopole. And again, in this case, we want to see up to which scale our model works, but also we want to assess the improvement that we get on the cosmological parameters when adding the bispectrum. So in this case, you can see that, again, some parameters are improved, others not so much. But I want to stress here that this is for the full 1000 cubic gigaparsec volume. So the power spectrum is already doing a great job. However, the bispectrum gives us some tighter constraints for some of the parameters. This is particularly important for beyond lambda CDM models, which is what I will show you next. So once we had our code working, we applied it to some data, and the state-of-the-art, let's say, data set that we have is the BOSS data. And this is a work done in collaboration with people at the University of Edinburgh. So first of all, we looked at the dark scattering model. This is a model that allows for momentum transfer between dark matter and dark energy. And it comes with two additional parameters, W and A, or W and Xi. This Xi, or A, is the strength of the interaction between dark matter and dark energy. So you can see here our results. In this case, we focused on the power spectrum, measured, this thing is dying, measured with a windowless estimator, as presented in the paper there. And what we found is, first of all, consistent results with lambda CDM, sadly or happily, depending on what your preference is. But we also found that there is a strong dependence on the priors that you put on the nuisance parameter. And this comes out particularly in models that have more parameters, so beyond lambda CDM models. This is because of the degeneracies between these additional parameters and the other parameters of the model. So in this case, in particular, the bispectrum can help in reducing the degeneracies. And this is what we explored in another paper with our student, Moretti. In this case, we used simulated data, and we wanted to see how much the bispectrum improved the constraints on these additional parameters of this particular model we looked at. So what you can see here, if you compare the MT red contours to the field red contours, the difference is power spectrum only for the empty one and power spectrum plus bispectrum for the field one. You can see that there is a significant improvement on the constraints of these two, which are the additional parameters of the model. In this case, it was about 30%. Of course, this depends on many things: the redshift you're considering, the volume of your survey, and so on. But in general, the ability of the bispectrum of breaking degeneracies in parameter space can be really important in the case of extended models. And so the last thing we did, this is a paper that we put out a couple of months ago. We did again the BOSS analysis, considering then another model. In this case, we used a commonly used parameterization for the growth, which is this gamma parameterization, combined with the presence of massive neutrinos. And again, we reanalyzed the BOSS data with the same setup that I described before. In this case, we also explored the impact of priors. And first of all, we found kind of consistent results with lambda CDM. So This is the additional gamma parameter, and this is the neutrino mass. The different priors that we try to apply are, first of all, no priors, so very broad flat priors on the cosmological parameters. And in that case, we also found very, very strong projection effects due to the degeneracies between parameters. And then we tried applying Planck priors on the primordial parameters, which were the ones most degenerate with our additional parameters. And in that case, of course, things work better, and everything is more well constrained and less degenerate. And then we also looked at forecasts for a stage 4 survey. In this case, we focused on a DAISY-like survey. So we produced synthetic data, mimicking for galaxy samples at, 3 galaxy samples at 3 different redshifts, and we analyzed them separately and then joined. And you can see here the results. The red one is the joint analysis. And in this case, we found a significant improvement on the constraints that we were able to put on the parameters, in particular on gamma. The improvement was more than 50% with respect to the equivalent BOSS analysis that we did. And for neutrinos, the result was a bit unsatisfying if the goal is to detect the neutrino mass. But this was obtained only using galaxy clustering data. So, of course, combination with CMB data or lensing data can improve this by a lot. We also found that the projection effects or the volume effects were much mitigated by the smaller error bars of this data set. Okay, I have one last slide, which is about Euclid. I am involved in the Euclid mission. This actually takes up a lot of my time. And in particular, everything that I described until now is very much relevant for Euclid, where I'm involved in the theoretical modeling for the power spectrum of the spectroscopic sample, and also in the likelihood analysis. And in the development of the likelihood pipeline that will be used by the Euclid collaboration on the data. So I listed here some of the projects that I'm involved in within the collaboration. We are doing Bayesian analysis, likelihood analysis of the flagship simulation, which is a very Euclid-like simulation in terms of density and volume of the simulation. I'm involved in modeling beyond lambda CDM models. So we're looking at massive neutrinos, evolving dark energy, and modified gravity. And then I'm a developer for the likelihood pipeline, the official likelihood pipeline for Euclid. So if you're interested in this, come find me later and ask me. I will tell you. So I think I'm out of time. Yes. So I will leave just my summary here. Thank you.